For our second try me problem, we consider problem 4-100 involving an atomic force microscope probe and a set of forces that are applied to the tip. And we'd like to find equivalent force systems at 2 points, at B and at O. And the problem statement states specifically to do this using a vector approach. Pause the video now and try the problem yourself, and resume playing when you're ready to see a solution. So the problem statement asks us to find the equivalent force systems using a vector approach. This problem is sufficiently simple that we could use either a scalar approach or a vector approach. So I'm going to do both. I'll start with the scalar approach and then we'll move on to the vector approach. So first, let's consider the equivalent force, the resultant force. That's quite simple because we have 3 force components each in the x, y, and z direction. So the resultant force is minus 5I plus 50J minus 10K nanonewtons. To find the resultant moment at B, we have a position vector that goes from B to A, and so we can see that the 50 nanonewton force component is going to be aligned with that and will contribute nothing to moments about B. Its line of action goes through B. So that gives us just the contributions from the 10 and the 5 nanonewton forces, and we can consider those individually. So we can see that between the position vector from B to A and the 10 nanonewton force, we are in a plane that's parallel to the YZ plane, so we know that the resultant moment is going to be in X from that contribution. And if I extend that position vector down and move my 10 nanonewton force this way and do my cross product, I'm going to find that that gives me a moment in the plus X direction. And so the magnitude of that will be 10 nanonewtons times 12 microns, which is going to be 120 femtonewton meters in the X direction. And so this prefix is femto. We have not run into that yet. It's the product of micro, 10 to the minus 6, and nano, 10 to the minus 9th, which gives us a prefix of 10 to the minus 15th. So we have 120 femtonewton meters in the I direction. And then this has gotten busy, so let me get rid of this and start over. And now consider the now let me consider the 5 nanonewton force. So again, I'll slide my position vector out and my 5 nanonewtons this way. Now I'm in the XY plane, so I know that I'm going to get a result in the Z direction. And if I cross R into F, that's going to give me a result that is clockwise and in the minus K direction. So that's 5 nanonewtons times 12 microns. It's in the minus K direction, so I have minus 60 femtonewton meters in K. To find the resultant moment using the scalar approach for moments about O, it can be helpful to first slide the 50 nanonewton force all the way up here and to consider this position vector, so I'll slide this over this way. We're going to take, again, R crossed into F, and that's going to give me a result in the Z direction. So there I've got 50 nanonewtons times 80 microns. That's going to give me 4,000 femtonewton meters in the K direction. And again, this is getting busy, so I'll get rid of this. And then for the 5 nanonewton force, I will slide this over in this direction. That's going to be also in the XY plane, and so if we are crossing this R into F, we're going to get a result that goes in the other direction. Here, this is going to be 22 microns times 5 nanonewtons. It's going to be 110 femtonewton meters, also in the minus K direction. And now for the 10 nanonewton force, we actually have two components associated with moments about O, one associated with this position vector, and we can see that that cross is going to give us a component in the j direction. That's going to be 80 microns times 10 nanonewtons. That's going to be 800 femtonewton meters in J. And then separately, we have this R cross F, which will be in the I direction, and will be 22 microns times 10 nanonewtons. That'll be 220 femtonewton meters in the I direction. So if we add all that together, our resultant moment ends up being 220I plus 800J plus 3890K femtonewton meters. Now, you may not have been able to see some of those cross products very clearly using the scalar approach, so let's go back to the original problem statement. So let's go back to the vector approach, and now we're going to make use of our position vectors RBA and then separately ROA, and we'll just do a cross product directly. So for a vector approach, at B we would say the moment about B is RBA cross FB. That's minus 12J crossed into minus 5I plus 50J minus 10K. Again, that's going to have units altogether of femtonewton meters. And so that's going to be 60 J cross I plus 120 J cross K. And we make use of the fact that J cross K is equal to I, and J cross I is equal to minus K, and that gives us the result 120 I minus 60K femtonewton meters. So we have the same result with the vector approach as we had with the scalar approach. At O, we have the resultant moment is ROA cross F. And now I'll go ahead and use our matrix notation for this. So that's (80) minus 22 and 0 for the position vector, minus 5, 50, and minus 10 for the force vector. And we end up with, in the I direction, we have 220 minus 0. We have a minus J times minus 800 minus 0. And then we have a plus K of 4,000 minus 110. And again, that gives us 220I plus 800J plus 3890K femtonewton meters. And that's the same result using the vector approach that we had using the scalar approach. So I'm going to avoid telling you that you must use either the scalar approach or the vector approach. I think, again, you're going to find that it's mixed, that there are some problems that are sufficiently simple that the scalar approach is a relatively straightforward thing to do. But if you are unable to use it, you can always go back to the vector approach, and that will always give you the right answer.